happy to be here to deal with this technology because I spent a lot of my time with this technology, and Europe is investing a lot in this kind of new technologies, not only for defense, not only for weapons, but also, I believe, mostly for civil application. Because of my company is mainly involved in defense, I will show you an example of defense platform in which photonics could be exploited, but Europe is strong in using photonics everywhere, or even in places in which we cannot see, like bridges. Fiber optic sensors are embedded in concrete pillar of bridges to sense the stress and strain status of bridges. This is a classical civil application of this new technology. Let me spend a few words about Finmeccanica. Finmeccanica again is a worldwide company involved in both sides of the industrial market, the civilian and military market, or as we say, defense market. And we are spread over the world. We are in US, in UK, in Italy, obviously, and we work in many different kind of platforms, in space, in airplane, ship, and also in the land system. This is the outlook of my presentation. I will speak about a little bit about what the photonics means, why photonics in systems, and I will show you some significant example of photonic application in platforms. What photonic is the places in which the photons and the electrons are used together to process signal or to make something in many ways. Here there are some examples of areas in which photonics is a significant an underpinning technology. For example, you probably know, I don't know the background of who is attending this conference, but I'm sure you know that fiber optic is fundamental asset in the communication. So we can say that fiber optic link is a photonic building block. But photonics is also in the optical interconnect at many levels. In the sensors, many sensors could be included in a photonic area. And also a new area which photonics is evolving is the quantum optics, in which we have the possibility to use photonics for quantum cryptography, but also to generate a new concepts for a computer. In this biography, I try to resume the way in which photonics impact in the iPhone platform. And again, we have an area in which the fiber optic sensors are exploited for monitor the status of the platform, but also to generate new sensors. But we have also the digital part of the fiber of the photonics, which is exploited for the data distribution, the secure communication, and the interconnection between subsystems. This is for who, I don't know if you know, this is the IFA, the Eurofighter, the Typhoon, the airplane built in collaboration among many European nations. So it's a classical example of how the Europeans can work together. And these are the areas in which photonics in this kind of platform could underpin the performance and generate a new capability. For example, in the center you can see the Earth monitoring, the embedding of the fiber optic in the composite structure or attaching fiber optic sensor to the is enabling to monitor the status of the part of the airplane in flight or during the maintenance phase. These are some features of subsystems in which photonics is exploited. In front of the airplane, you can see the front, the nose radar, in which the fiber optic I will show you is has a very, very significant impact in terms of performance and new capabilities. Why photonics is very simple. The possibility to use photons in place of electrons enabled the platform to be much more immune to electromagnetic interference. And also we can reduce weight and volume of subsystems. We can, as in the case of optical communication, to exploit the capability to manage a huge digital data, huge quantity of digital data in a very small dimension. The fiber optic dimension is less than 100 micron in terms of diameter. We can also exploit the capability to be low loss, but in terms of processing, you will see what I mean in terms of processing of for example, of radar signal. We can manage a very wide instantaneous bandwidth because the carrier is so high frequency that the frequency bandwidth in the radar region is, relatively speaking, is very, very narrow. We can process the signal in real time, and we can get also very high accuracy, resolution, and performance of the system. Now some example of photonic application. The first one is the use of fiber optic grading in structural health monitoring, and we can use the fiber optic embedded in the structure to perform both prognosis and diagnosis, and we can anticipate the catastrophic failure of the part in flight, but more important in terms of economics, we can relax the constraint to, in other words, we can increase the time in which we are obliged to test the structure for maintenance. Now, for example, military airplanes are obliged to be completely tested, even I don't remember exactly the time, but a certain amount of flight hour. Using this kind of sensor, it has been demonstrated that it is possible to extend this time range of 2 times or even 3 times, and reducing a lot of the cost of maintenance of the platform. This is how the sensor works. In the fiber optic is impressive grading. The grading is impressive using ultraviolet light, and the fiber is embedded in the composite structure and follow the status of strength and strain of the structure. And when the fiber optic is compressive or stressed, the period of grading increase or decrease, so the wavelength reflected by the grading change, and measuring the change of the wavelength, the shift of the wavelength, you have an instantaneous measurement of the status of the stress and strain status of the part. And at the top on the right, on the left, you can see the section of the fiber embedded in a composite structure. The other material are epoxy and carbon fibers. And we are exploiting this kind of sensors inside the wing of the Typhoon, but also inside the barrel of the military transport new airplane, the C-27J. And we are achieving a significant performance.